So the last cool thing we'll do with Markov chains is what we call hidden Markov models. And what happens with these is you have some background information that you might not be able to observe, and then some foreground information that you are observing. And can you conclude anything about the background stuff from the foreground stuff? So one cool example of this is facial expressions. So the observable thing is people's facial expressions. And the thing that's going on in the background is their emotions. You can't observe their emotions, but their emotions are what's actually changing from day to day. And we pretend that someone's either happy all day or sad all day, and those are the only two emotions. Gross oversimplification of what's going on. So if you're happy, you have a 2/3 chance of being happy tomorrow, 1/3 chance of being sad. And if you're sad, you have a 1/2 chance of being sad again, and a 1/2 chance of moving to happy. You can't observe if someone's happy or sad, and you can ask them, but that's kind of a strange question in today's society for some reason. What we can observe is if someone's smiling or frowning. So, if the person's happy, they have a 3/4 chance of smiling and a 1/4 chance of frowning. More likely to be smiling. And if someone's sad, they can also be smiling or frowning, but maybe they're faking, so they're not doing it too often. They have a 1/6 chance of smiling and a 5/6 chance of frowning. You can't observe their emotions. You can observe whether they're smiling or frowning. So one thing you might ask is, if someone is smiling, what's the probability that they're happy? Probably pretty high. This sad thing isn't happening too often. Okay, how would you answer that? Okay, well, let's make a transition matrix for the original Markov chain, which eventually you might not have this information, but for now we do. So we've got happy, we can be happy again with probability 2/3, sad with probability 1/3, and then sad, we're happy with 1/2, and sad with 1/2. And if we looked at the eigenvalues, calculated the eigenvalues, we would get 1 and 1/6, and we mostly care about the eigenvector corresponding to eigenvalue 1. We get 3, 2, or if we scale that, we'll scale it so that the column vector adds to 1, 3/5, and 2/5. Okay, so what does this say? This says if we run this, sorry about that, if we run this enough, then you have a 3/5 chance of being happy, 2/5 chance of being sad. And so at least you're happy more often than you're sad. That's good. Great. Now, if someone is smiling, what is the probability that they're happy? Okay, so what is the total amount of time that they're smiling, or total percentage of time, fraction of time? Well, they're happy with probability 3/5, and when they're happy, they're smiling with probability 3/4. And they're sad with probability 2/5, and when they're sad, they're smiling with probability 1/6. That's the total fraction of time they're smiling. And then we care about the ones that we want are smiling and happy. So 3/5 times 3/4. I'm sure you could word this as a conditional probability, but I think it's cooler to just think about it like this. Okay, and then we calculate it, and I think it works out to about 0.87. Okay, so you're smiling. If you're smiling, then you have an 87% chance, approximately, of being happy. We can ask a lot more interesting questions, like if you observe someone smiling 4 days in a row, what's the probability that they're happy? Might be a cool question. Or eventually, you're going to only observe smiling and frowning. So you can make a new Markov chain, and really you shouldn't know this original Markov chain. You would only know the new Markov chain. What is the probability if they're smiling one day that they're smiling or frowning the next day? And if they're frowning, what's the probability that they're smiling or frowning the next day? And could you take this Markov chain and recover any of the original Markov chain? That is the fundamental question when you're working with hidden Markov models. So you answer some of these in your homework.